Well, after the lectures on the balanced block designs, we'll begin a series of lectures on the factorial and fractional factorial designs. There's a pretty class of designs, the fractional factorials. Now, they're very important when it comes to screening for the important variables. This is a very common problem. You're following some sort of a response, and the trick is, of all the variables that you can control, and there may be a great many of these variables, which of these variables has the biggest impact on that response? Let me cook up an illustration. Suppose you were measuring the moisture in a cake. You had some method for determining the moisture in cakes. And now think of all the different variables that go into making the cake in the first place. There's the mixture of the flour, and the baking powder, and the amount of milk, and the number of eggs, and the amount of shortening, and let's see, whether or not you mix it, and how much you mix it, and so on and so on. The amount of salt, the amount of sugar, how long you let it stand before you put it in the oven, what the temperature of the oven is, how long it stays in the oven. And if I really knew something about cake baking, I could enumerate a large host of variables, all of which could contribute to the response. In other words, the moisture in the cake. Now, which of all these many variables are most important? Okay, how would you proceed? And you will find with the fractional factorial designs that we can, with remarkable economies in the number of runs, ferret out of all the candidate variables that subset which are having the biggest impact on the response. These designs are simple to organize and very simple to analyze, and it's worth your while to hear about them. And then, of course, there are the factorial designs. These are probably the most frequently employed designs in industry. In this instance, we're trying to figure out, for example, if I change the temperature from one level to another, what's the effect of temperature on the response? By how much does the response move as I change the temperature, or as I change catalyst from catalyst A to catalyst B? And we'll find out the factorial designs give us a strategy for simultaneously, key word, simultaneously studying several variables in an effort to determine their effects and to determine their interactions. And so we'll spend a lot of time on the factorial designs as well. And then finally, the remaining 6 or 8 lectures will be involved in what is generally called response surface methodology, or more or less sort of obvious applications of least squares. Here's a situation in which the experiment is trying to construct an empirical picture or a graph or illustration of how the response changes as he changes a variable under his control, a continuous variable under his control. Well, let me give you an illustration over here on the board of just what I'm about. Speaking in somewhat general terms, here's a controlled variable psi. That might be temperature or time or pH or voltage or what have you, some variable that you can control. And here's the response variable eta. And you'll notice as I change psi, the response goes up and comes back down again. Now, here's the problem, gang. You don't know that response function. It's unknown to you. And instead of seeing that response function, what I want you to imagine is a large smear of observations. You see, you won't really see the true response. You'll see the response disturbed by error. So all the way along there's a smear, if you will, of observations. And to make the problem even more difficult, instead of seeing all those many, many hundreds and hundreds of observations, all you're going to get is a small collection, just several observations along the line. And they're going to vary about the line. And now you have your problem. Right? Can you, with these variable and limited numbers of observations, unfold the true nature of that response function? That's a good question. And what we'd like to do is show you some of the strategies that are evoked in order for us to fit lines of various complexities. Now, we don't have to do all this relative to one response variable and one control variable. We can have more than one control variable. Here's a situation in which there's a response variable, in this case the yield of a chemical process, as a function of temperature and the concentration of one of the reagents. And you can see as I go up in temperature, I go up in yield, and as I go up in concentration, I go up in yield, and if I go up in temperature and concentration simultaneously, I get that sort of surface, that curved surface of yields. I didn't have to illustrate it with that kind of a diagram, since I'm talking in terms of surfaces and so on. I might just as easily have illustrated all that by a contour representation. We see the very same surface displayed here in a contour diagram. See, here's temperature and concentration again. Everywhere along that line, the yield is 60. And everywhere along that line, the yield is 65. And so you ought to be able to see with that contour representation the curved surface that we just illustrated a moment ago. Well, there are lots of different kinds of surfaces you'll run into. What do you say we look at a planar surface? Here's an illustration. The contour lines are parallel straight lines. You see, as I go up in temperature, I go up in yield. The response goes up. As I go up in concentration, the response goes up. As I go up in temperature and concentration, the response goes up in a very uniform fashion. I have a planar response function. Here the yields are 70, and here they're 60, and here they're along here 50s. So that's a picture of a planar response function. As I vary the two variables, I get a planar response. Of course, you could get a curved response function. Here's a picture of a hill, if you will. There's a possibility of very high yields in the high 80s right through in there. And one of the problems of experimentation is to find the location of the optimum level of x1 and x2, the two variables under our control, so that we get the best yields. This gives me a chance to sort of illustrate one of the interesting strategies that crop up if you use response surface designs and response surface attacks and so on. Let's take the following curved surface that you see here. It's a rising ridge. See it? All the yields here are 76, and all the yields here down here at 72. One very popular experimental strategy, which we often use in such a situation, is called one factor at a time. And the experimenter begins as follows. He says, well now, I think I'll hold x2 fixed and vary x1. So holding x2 fixed, he starts running experiments along in the x1 direction, keeps increasing x1. As he does, of course, he keeps getting higher and higher yields. He'll locate that point there where the yields are very high, and then, of course, he proceeds along in the x1 direction, the yields start falling off. He says, by golly, that's a very good level of x1. So what do you say I'll hold that level of x1 and vary x2? So if I come down in the levels of x2, whoops, there go the yields. And if I go up in the levels of x2, the yields tumble again. And so the experimenter ends up believing that there, by golly, are the very best yields indeed. Whereas his competitor started off at a different place. And by starting off at a different place, he would have converged onto another location on that rising ridge. And so this is why we are really interested in having a strategy of experimentation that doesn't sort of give you a false impression as to where the maximum or the highest yields are. What we'd really like to have is a picture of that ridge. Okay, let's go through a brief example. And here we see on the board the contours of a curved response function. And our objective in this instance is to locate the levels of time and temperature which will give us the highest yields. Now, before running this experiment, the experimenter thought that this region down here, between 50 and 70 minutes and something less than about 50 to 57.5 degrees and so forth, was the very best operating condition. That's his best guess. And so he puts down that small pattern of experimental points. Let's see what the observations looked like that he obtained as a consequence of running those 5 environments. Here they are. Okay, now our purpose is to use these data to draw a picture of the nature of the response function. And really, we'll find out a plane does a pretty good job of manifesting the unknown response function here. You notice you go up in time, you go up in yields, you go up in temperature, you go up in yields, and the improvement seems to be reasonably steady state over the entire experimental region. By a very, very simple calculation, you can actually plot the contour lines of the best fitting response function, and we see those right here. There are the contours of the best fitting plane. Now, since we're anxious to get to high yields, what we do is move perpendicular to those contour lines along something called the path of steepest ascent. And we see that path of steepest ascent here. Incidentally, you will notice that these contour lines we drew down here for the best fitting plane aren't exactly what's going on, but they are a reasonable representation of what's going on in that experimental region. Enough, in a sense, to engineer progress out of that experimental region into alternative experimental regions. Well, here we go. He does experiment 6, gets yields in the high 70s. He takes another step on the path, comes up here to experiment 7, gets yields in the very high 80s. Takes another step. Gets yields down below 80. And so he feels in the region of 7, things are looking pretty good. What do you say we put down another pattern of runs in this particular experimental region? Here are the runs he obtained. Now, there are some exact methods for doing the following, but anyone can eyeball that data and see right away that a plane is not going to fit the data. At the low temperature, if I go up in time, I come up in yields. At the high temperature, if I go up in time, I go down in yields. A plane is not going to fit that data. We will find we'll have to augment the information we currently have by additional data points, and we see those additional data points here. Here are the 5 original environments, and here are additional environments which we organize and take. Now, to reduce that data into a reasonably understandable form, it takes a bit of calculating, but we can see the consequences of our analysis here. Here are the contour lines which we can construct on the basis of those 9 experimental environments. You can see all the way along here the yields are 87.5. All the way along here the yields are 85, and so on. And you can actually see a curved surface there with higher yields up in this direction. It's very interesting indeed to see what the experimenter has uncovered about the nature of the response function as he's done this sequential exploration. And we see them right here. Down here he got an approximating plane, which he was able to use to get out of that experimental region into regions of higher yields. And up here he has a picture. Not exact, but certainly useful, showing what the nature of the response function is in that area. And so here's an experimental strategy which permits you to move through the factor space to find the optimum yields. And I'll tell you now the real problem. Suppose instead of having 2 variables, time and temperature, you had 4 variables you wanted to study simultaneously and their effect on the response. Tell me now, how would you tool around in that factor space most resourcefully to find the optimum yields? And we'll show you how these strategies of the experimental designs using in sequentially small blocks of runs will unfold the essential characteristics of the unknown response function regardless of how many variables you're dealing with. Now, of course, with these more advanced designs, the use of a computer would be very, very important indeed. But the point I really want to make is that for 80 or 90% of the work that we're going to do in this particular course, you don't need a high-speed computer. A desk calculator or pad and pencil are really all that is necessary to use these statistical methods. Or you say, well, by golly, if it's all that simple, why at this late time in my career am I taking a course in statistics? Why didn't I get this when I was an undergraduate? And the answer to that's easy. The arts of statistical design were cooked up by the biologists and agronomists. Imagine the problem of the agronomist when he sets out his crops to test which varieties are better. The errors impinging on that data-taking process are tremendous. The weather, and rabbits come scurrying across the fields and eat them up, and all kinds of things happen to that sort of experimentation. So they learned how to take data in the presence of large errors. This happened in the late 20s and early 30s. And now trickling down into the scientific environments and so forth, our courses on design of experiments. And the men coming out of the colleges and universities are going to have more and more of this kind of education as time goes on. But what is the real purpose behind our teaching you these statistical methods? Well, what's the purpose of statistics in the first place? The purpose of statistics in the first place is to analyze the data in such a way as to lead to new conjecture. Now remember what we're up against. The data are expensive, and the data are variable, and we don't know the true response function, and yet we have to go through this particular operation. All of this is part and parcel of the arts of statistics, but they're really not very valuable unless we can call upon the experience that people such as you have, which comes only from working in an industrial environment. And our real objective is to wed together your experience with the practical uses of engineering and production and development and research with the arts of statistics, so that you'll be more valuable to yourselves and you'll be more valuable to those you work with.